today's video, we're going to describe the transformations of exponential functions. All exponential functions can be written in the form f of x equals a times b to the x power plus c, where a is the initial value, b is the common ratio, and b is what tells us if the function is exponential growth or if it's exponential decay. So if the value for b is greater than 1, then we know our function is exponential growth. And if the value for b is less than 1, then we know our function is exponential decay. Now, something that's apparent in every single exponential function is a horizontal asymptote. It's that imaginary line, because it's not a line that we graph, but it's an imaginary line that the function will continue to approach, but it'll never, ever, 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 ever quite hit that value. And then domains for exponential functions are all real numbers. I didn't talk about the range yet, but we're going to look specifically at the ranges of these functions that we're going to be describing the transformations of today. So our parent function for today's lesson isn't really the parent function for exponential functions, but we are going to use it as the function that we're transforming. The initial value for this function, where f of x equals 2 to the x power, or we can also say y equals 2 to the x power, is 1. The initial value, or you can refer to it as the y-intercept, is 1. The common ratio for this function is 2, which means we are looking at a function of exponential growth. The domain is all real numbers, and the range is all y values such that y is greater than 0. And then our horizontal asymptote here is y equals 0. The function looks like it's going to get extremely close to y, maybe even hit y, but it never actually reaches any y value equaling 0. So for our first transformation, all we're doing to the parent function is putting a negative sign in front of it. Right, so our function for this is y equals negative 2 to the x power, but there's no parentheses there. So our initial value is a negative 1, and you can see from the graph that this function crosses the y-axis at negative 1. The domain is, again, all real numbers. The common ratio has not changed. This would be an exponential growth function. However, because there is a minus sign in front of it, because that initial value is negative, our graph is reflecting over the x-axis. So it looks like it could be exponential decay. So it starts really, really close to 0, but then exponentially decreases and shoots down. The domain, still all real numbers. The range for this, because a is negative, the range for this is all y values that are less than 0. And then the horizontal asymptote for this is still 0. For our second transformation, we're looking at y equals 3 times 2 to the x power. So all we've done to the parent function here is we've multiplied it by 3. So instead of our initial value being 1, like it was in the parent function, now it's 3, because we have a coefficient in front of b. We have a value for a. Our common ratio is still the same. It's still an exponential growth function where the common ratio is 2. And the domain of this is still all real numbers. So all of the x values is your domain. And the range here is all y values that are greater than 0. We still have the horizontal asymptote y equals 0. So the range here is all y values greater than our horizontal asymptote. For transformation 3, we're looking at the function y equals 2 to the x power plus 1. So a couple things have changed here now that we have a horizontal asymptote added to our function. Normally we can look at our exponential function, look for the value of a, and we can immediately say that is my y-intercept. That's my initial value. But you have to be really, really careful when you have a function that has a horizontal asymptote. So I'm first going to point out what the horizontal asymptote is for this function, right? So because we have a value that's added to the function, which in this case is plus 1, our horizontal asymptote is 1. So that means the range for this function, because it is an exponential growth function, is going to be all y values that are greater than 1. The function looks like it will eventually touch a y value that's equal to 1, but it gets ever so close to that and it never actually touches y equals 1. The domain is still all real numbers. The common ratio still 2, so we still knew it was an exponential growth function. But what makes this different is our initial value. Our initial value in this case is 2, even though there is no a equals 2 that we can take from our function. The reason why the initial value is 2 is because our horizontal asymptote is 1, which moved our entire graph 1 unit up. So that means my initial value is also going to go 1 unit up. So from the function, I would assume that the initial value is 1, but I need to add my horizontal asymptote to that as well. So 1 plus 1 gives me 2, which is my actual initial value for this function. So to look at another function like that previous one, only thing we changed in this function versus the parent function is that we subtracted 2 from the parent function. So our function here is f of x equals 2 to the x power minus 2. So we could assume just from that function that our initial value was going to be 1. Let's just move down the line and come back to that initial value, because you can see I wrote that the initial value is negative 1. And we can see from the graph that the initial value is negative 1. Our common ratio, still the same. Common ratio is still 2. Domain, still all real numbers. The range is different. Because our horizontal asymptote, which is our value for c in the function, is negative 2, our range is all y values that are greater than negative 2. And so what that means for our initial value, since I have that horizontal asymptote, I would assume from the function that my initial value is 1, but because my horizontal asymptote is negative 2, I need to go down 2 units. So 1 minus 2 gives me negative 1, which is my actual initial value for this function. For transformation 5, this is probably the most complex transformation we're looking at, but it's really what happens if you have something present in your function for a, b, and c. So with our parent function, we've really just had a value for b, which was our common ratio, but for this, we're throwing in a value for a, and we're also throwing in a value for c. Our common ratio here stayed the same. Common ratio is 2. Our domain, all real numbers again, so all x values. Our range here, because we have a horizontal asymptote, which equals negative 2, our range is all y values that are greater than negative 2. Now our initial value, from our function, we would assume the initial value is 3. So we would assume that on the graph, we should see that on the y-axis, there's a point plotted at 3. But because the horizontal asymptote is negative 2, I need to combine my assumed initial value with the horizontal asymptote, which gives me my actual initial value, which is positive 1. So that is why a equals 1 in this function. So that's it, everyone. I hope you enjoyed this video. Don't forget to like, share, and subscribe, and check out the description below for a link to other videos in this series, and I'll see you guys next time.